Welcome to our presentation on vehicle localization systems based on sensor fusion. This presentation was prepared by myself and my two group members, Grant and Johnson. This presentation discusses the what and why of vehicle localization, the techniques used, sensors, sensor fusion, Kalman filters, and neural networks. What is vehicle localization? It is the use of sensors to measure the dynamic states of the vehicle. It can provide the position, orientation, velocity, and acceleration information. Why is vehicle localization important? Well, it aids in navigation, route planning, and safety. There are two types of localization used on autonomous vehicles. The first type is the Global Navigational Satellite System, which is an absolute or global localization. GNSS relies on satellites to determine the location of the vehicle. The problem arises when the vehicle cannot connect to the satellites due to physical obstructions, such as mountains, buildings, or tunnels. Depending on your physical location in the world, different satellite networks will be used. In North America, the predominant system is the Global Positioning System, or GPS. IMU is a relative localization system. It relies on various sensor measurements from the vehicle to determine the relative location of the vehicle. GNSS is quite useful, however, it does have drawbacks. Now, the advantages of GNSS are that it can identify your location on the Earth. This is important because knowing your location within the global coordinate system provides a starting reference point for IMU localization. The second advantage of GNSS is that it is not susceptible to sensor drift. Sensor drift is the low frequency change in a sensor with time. It can be attributed to electronic aging of components and reference standards in a sensor. If a sensor drifts smoothly, the drift can be corrected and accounted for. The disadvantages of GNSS are that it is prone to noise error due to physical obstructions such as buildings, mountains, and tunnels. GNSS only provides a position. It cannot determine orientation. GNSS also suffers from a slow update rate. Consumer receivers typically have an update rate of around 1 to 5 Hz, and professional receivers are around 20 Hz. Despite the disadvantages, the GNSS localization system is a crucial part of autonomous vehicle location. Inertial measurement units, localization, relies on accelerometer, gyroscope, magnometer, and odometer sensors to aid in localization. IMU offers advantages including low noise and the ability to determine orientation. The disadvantages of IMU localization are that it cannot determine your location in the global coordinate system, and it is prone to sensor drift. Now, this sensor drift can be accounted for, provided that the sensor drifts smoothly. It is worth noting that the shortcomings of one localization system are addressed by the other system. For example, IMU cannot locate you on a map, but GNSS can. And GNSS cannot determine your orientation, but IMU can. Now, this illustrates the need to combine the different localization systems. Combining the two localization systems provides a more robust and complete overall system. The combination of the two systems is accomplished through a process called sensor fusion. Since individual sensors have some degree of uncertainty, which ultimately contributes to increased error, sensor fusion is necessary to provide a localization system that has less uncertainty and lower error than could be accomplished through independent sensor measurements. Additionally, if one sensor fails, it can be compensated for by the other sensors. Incorporating redundant sensors serves to further increase the accuracy of the overall localization system. The actual process of fusing the sensor measurements can be accomplished by two different methods. One is through the use of a Kalman filter, and the other is through neural networks. The main advantage of sensor fusion is that it provides a localization system that is greater than the sum of its parts. The Kalman filter is the traditional method for localization data fusion in vehicles. It was first used in the Apollo program for the trajectories of the spacecraft. The Kalman filter is a special type of filter that uses a dynamic model of a system along with control inputs and measurements to form an estimate of the system states. Typically, Kalman filters can be thought of as operating in two distinct phases, predicting and updating. The predicting phase uses the previous state information along with the dynamic model to predict the next state. In the updating phase, sensor measurements are combined with the predicted state to produce an updated state. This updated state is then used in the next iteration of the predicting phase. The Kalman filter works to smooth out errors in measurements, but it encounters difficulty with nonlinear dynamics. A neural network is a set of algorithms that aims to recognize underlying relationships and patterns in a set of data. The process is similar to the way that biological neural networks operate in animal brains. Neural networks are a newer method for handling sensor fusion. The neural network is usually less complicated to design and can deal with nonlinear systems much better than the Kalman filter. However, a large, robust set of data is required to train the neural network. GNSS and IMU are two localization systems used for vehicle localization. By combining them through sensor fusion, a very robust localization system can be created. The Kalman filter is the traditional method of sensor fusion, but it has its limitations. Neural networks, on the other hand, which are a new method of sensor fusion, have the potential to become more widely used as technology advances. Thank you for watching our presentation.